Hi everyone, this is Peter Yoachim. I'm here to give you an update on kind of the progress the Rubin Observatory scheduler has made in the last year. So if you're one of those folks who just pops into the scheduler session every year at the PCW, this is your update. So at last year's PCW, we'd made it about halfway through the list of recommended simulations from the Science Advisory Committee, and we just released version 1.2 of our simulations. Currently, in the last year, we've had 4 releases. Just now we've released 30 simulations for version 1.6, so that's a couple hundred simulations in the last year. We've generated a report for all of these simulated surveys to the SCOC, the Survey Cadence Optimization Committee. You can see the link there if you'd like to read it. It's like an 80-page report, so I'll just give kind of some highlights of new things we've developed. We have more in-depth talks talking about the details of those simulations and the results. So we've worked on some algorithm improvements in the last year. One of them is kind of improving how we select areas of sky. The main way we observe is during dark time is to select kind of a large block of sky that'll take about 20 minutes to observe it, switch filters, and then observe it again. And so on the left here, you see version 1.4, a single night. This is an alt-as projection, so zenith is at the center. And on the right is version 1.5, where we have added a constraint to try to keep areas more contiguous. And hopefully you can see that observations are kind of packed a little more closely together. There aren't as many spread out single observations. And so that results in lower slew times as we go from pointing to pointing. Here are the slew time histograms from those 2 simulations now over the full 10 years. Notice that it's a logarithmic axis on the y-axis there. So we're very peaked at about 4.5 second slews, but by making areas more contiguous, we did bring the mean down from 8.5 seconds to 7.7 seconds, and that's enough to upgrade from 2.18 million observations to 2.2 million observations over 10 years. So we get a nice little couple percent boost in the number of observations when we make areas more contiguous. That also means we get more overlap between observations, so short time scale science gets a boost when we've made this improvement. Another change over last year is we've moved the location of the 5th deep drilling field. The project has announced 4 deep drilling fields. Those have stayed the same, but we had a 5th one in there because we always assumed there would be a 5th field, and now it's looking more like it will be the Euclid Deep Field South, which is actually a double pointing. So there you can see the location of the old deep drilling field that was kind of a placeholder on the left, and then on the right, that double Euclid field that we've added as the new baseline. Another upgrade is we've changed how we track survey progress in the scheduler. Before, we would define a footprint, like this one here in the R-band, to say this is what we want the survey to look like, and the scheduler would go and try to maintain a survey footprint that looked like that. And the problem is, at the start of the survey, of course, not all the sky has even been visible yet or has come into season yet. And so the scheduler would think areas of the sky had fallen behind when really they couldn't have even been observed yet. So we've upgraded this map to be time dependent. And so now instead of a single static footprint, our footprint evolves with time like this. So there in the upper left, you can see night 1. We only want the scheduler to maintain a footprint that would have been possible for night 1. And as time progresses from left to right, top to bottom, you can see after 361 days, it looks almost exactly like it did before. And so now the footprint is maintainable and actually reasonable. And what this does before, here's an alt-as projection of all the observations. We would have a skew a little bit towards the east, and just because we were always trying to catch up on these fields that seemed like they were behind but weren't actually behind. And now if I flip ahead to the new simulation, it's a very subtle shift, but it actually is slightly more symmetric, and our median depths in most filters goes up 1 to 2% just by being a little more symmetric about the meridian. So it's a modest improvement in the baseline, but it actually makes a huge difference when we do rolling cadences. So before, here's a rolling cadence where we divided the wide, fast, deep region into 6 declination stripes. And you can see the wide, fast, deep area is not perfectly uniform. There are these 6 overexposed stripes on the left there. And so when we switch to a time variable footprint, it disappears. Here's the new simulation, and now wide, fast, deep is perfectly smooth, even though we've done a rolling cadence. And I'll point out this had a bug in it, so the north ecliptic spur lost some observations there. But here's where there wasn't a bug. So this is comparing the baseline with a rolling cadence again. So the top lines show after 10 years. Both of them have very, very smooth wide, fast, deep regions. And on the bottom, I'm showing just a section of 1 year. And so the baseline is a uniform survey all 10 years. It looks uniform. However, the rolling cadence, we have these declination stripes of heavy and light observations. And so on the next year, that pattern will flip so that after 10 years, it adds up to smooth. But now we can do very high sampled light curves for some of the sky and still have that smooth distribution at the end. So static science shouldn't be impacted at all if we want to do rolling cadence. Another aspect we've been working on is continuing to develop science metrics to analyze the output of our simulations. Some of the things we've come up with some new tidal disruption event metrics. The Dark Energy Science Collaboration has been hard at work generating lots of metrics that are being incorporated. The Solar System Collaboration has been updating their solar system populations and running their metrics. We've got a new microlensing metric that uses improved stellar density maps, so we can look at how well we think we'll recover microlensing events. And of course, if anyone has a science metric they'd like to contribute, we are always looking for them. All right, we got a little distracted this year by Starlink. We were concerned about how Starlink could impact Rubin observations. So for those of you who don't know, Starlink is a planned mega constellation of tens of thousands of satellites in low Earth orbit that will be a communications network. There's the plans of what such a mega constellation would look like. Here's an image from DES where they caught some of these satellites on their way up. And you can see lots and lots of streaks from those satellites in the image. So we ran some simulations checking, generating a realistic Starlink network and seeing how many observations of Rubin would have streaks in them. And there's some plots showing the results. The main takeaway is that in summertime, there are illuminated satellites all night long. We were hopeful that maybe it would just be around twilight, but in twilight and even an hour after twilight, there are lots of illuminated satellites in the sky. Wintertime, in the middle of the night, the sky is clear, but the rest of the time we will definitely have some satellites. The good news is these satellites should not saturate images. So there will be streaks, but they're not saturating, so they're not going to blow out like entire CCDs worth of data. A lot of people say, but you know where the satellites are going to be. Why can't you just dodge them? At twilight, there are just too many. Our field of view is so large, there's really no place to point the telescope to avoid them completely. At other times, you need to know the orbits of the satellites and the kinematics of the telescope incredibly precisely to be able to avoid them. And this gets tricky because we like to take observations in pairs to get moving solar system objects. It's not enough to say, this spot of the sky will be clear of satellites. We need it to be clear now and clear 20 minutes later, and be sure that our kinematic model will return us there exactly 20 minutes later. If we're off by several seconds, that's enough time for a new satellite to move in. So it's really hard to choreograph a night down to the precision we need to completely avoid all the satellites. There are some things we can easily do to reduce the number of satellite streaks a little bit, but complete avoidance is going to be very, very tricky unless we want to spend a lot of time slewing the telescope and then we lose efficiency. So for example, here is, after twilight, the sun is below negative 18 degrees altitude. This is a 10-minute exposure of what the satellite streaks on the sky could look like. That dark region on the left is Earth's shadow coming in. However, that's very high air mass beyond our altitude limit. So even from here, we can see there's some regions, like this box region, where if we decide to point there, we will have many fewer streaks. So we can reduce the streaks, but eliminating them completely is going to be hard. SpaceX is actively collaborating with us, looking at different scheduler options, and they are trying to darken their satellites a bit so that they're extra sure they won't saturate our images. All right, so in conclusion, we released a lot of simulations based on the Cadence white papers and the SAC recommendations. Those are out. We'll have more talks detailing those. The report is submitted. We've made some algorithm improvements, finding a couple percent improvement here, a couple percent improvement there. We're continuing to develop science metrics to judge survey strategy, and we're looking at how we can avoid satellites in the mega constellation era. If you have any questions, our session is going to be Wednesday. Look at that link for the Zoom details if you want to call in and ask, or you can always ask questions on community.lsst.org, and you can tag me and I'll see it and answer it. All right, thanks.